Hydrides of group 15 elements. Hydrides of group 15 elements have the general formula EH3, where E is the group 15 element. So the hydrides can be written as NH3, hydride of nitrogen, ammonia. Then hydride of phosphorus, phosphine. Arsenic hydride, arsine. Antimony hydride, stibine, SbH3. Bismuthine or bismuthine, the hydride of bismuth. Hydrides of group 15. All the hydrides of group 15 are bases because they contain one lone pair electron on the central atom. So all these hydrides carry a lone pair electron on the central atom. Hence they are all Lewis bases. They are electron rich. They can act as electron pair donors. All the hydrides have the shape trigonal pyramidal. Hydrogen atom at the corners of a trigonal plane with the group 15 element at the apex of the pyramid. It has got a pyramidal geometry, trigonal pyramidal geometry. The central atom, the group 15 element, contain a lone pair electron. That's why they are Lewis bases. We can compare the basic character, basicity of the hydrides. When you compare, we see that ammonia is the strongest base. Ammonia is stronger base than phosphine, than arsine, than antimony hydride, than bismuth hydride. Strongest base ammonia, weakest base bismuth hydride. This is due to the lone pair electron density. Lone pair electron density is maximum on nitrogen because nitrogen the smallest size. Because of small size, the electron availability, lone pair electron availability per unit volume on nitrogen is maximum. Bismuth being larger, the lone pair electron density or the availability of lone pair electron per unit volume on a large volume of bismuth is minimum. Hence, ammonia is the strongest base, bismuthine is the weakest base. We can also compare the bond strength. Group 15 element hydrogen bond strength, which is directly related to the bond enthalpy, that is delta H dissociation enthalpy of EH bond, which is also related to the stability, thermal stability. All these are directly related. So all these follow the same order: bond enthalpy, bond strength, thermal stability. Down the group, we know size increases. Size of the group 15 element increases from nitrogen to bismuth. As the size increases, electronegativity decreases. So the bond strength decreases actually. So how the variation of bond strength or bond enthalpy or thermal stability? Bond strength down the group decreases. Bond enthalpy decreases. Thermal stability also down the group decreases. Means the same order as basicity. Basic character down the group decreases and these also down the group decreases. Means we get the same order. That is NH3, the bond is strongest. Bond enthalpy maximum. Thermally most stable than phosphine, than arsine, than antimony hydride, than bismuthine. This is the order of bond strength, bond enthalpy or thermal stability. Down the group, as the size increases, electronegativity decreases, bond strength, the strength of the bond between group 15 element and hydrogen decreases. Stability also decreases. The next property is regarding the bond angle. If we compare the bond angle of these hydrides, the bond angle of the hydrides also decreases down the group. Down the group, bond angle also decreases. That means the same order. In ammonia, the maximum bond angle, and the bond angle minimum in the case of bismuth hydride. Means the order of bond angle also the same. Down the group it decreases. This is due to, in the case of ammonia, nitrogen which is bonded to 3 hydrogen atom, nitrogen being smaller in size, nitrogen being small size and highly electronegative, the bond pair electron shared between nitrogen and hydrogen are closer to the nitrogen atom. Because nitrogen is small size and more electronegative, the electron pair, the bonding electrons lie closer to the nitrogen, so they feel more repulsion. The repulsion between the bond pair electron will be maximum in the case of nitrogen, and hence the bond angle largest. Ammonia is having the maximum bond angle and the minimum bond angle for bismuth hydride. This is because bismuth being larger, the bond pair electron shared between bismuth and hydrogen atoms lie at a far distance from bismuth. Means the repulsion between the bond pairs will be less, bond angle minimum. Ammonia has maximum bond angle, bismuth has minimum bond angle. Bond angle down the group among the hydrides decreases. If you take the next property, that is reducing character, that is ability to act as reducing agent. Reducing character of these hydrides. Reducing character can be explained in terms of the ability to donate hydrogen. If the bond between group 15 element and hydrogen is weak, it break readily and donate the hydrogen easily. So which will be the strongest reducing agent here? The one having weakest bond with hydrogen. The weakest bond with hydrogen is for bismuth hydride. Hence the bond between bismuth and hydrogen break easily and the hydrogen can be easily donated. So bismuth hydride is the strongest reducing agent. The bond between nitrogen and hydrogen is very strongest. Difficult to break and difficult to donate hydrogen. That means ammonia is the weakest reducing agent. That is, the order is just the opposite. That is NH3 weaker reducing agent than PH3, than arsenic H3, than antimony H3, than bismuth H3. Bismuth is the strongest reducing agent. Ammonia is the weakest reducing agent among the hydrides of group 15. Now let us compare the next property, boiling point. Boiling point of group 15 hydrides, if you compare, we have studied boiling point directly related to the molecular size or mass of the compound. Greater the size, stronger the van der Waals forces of attraction and higher the boiling point. So the expected order of boiling point is ammonia with the nitrogen the smallest size, we expect smallest boiling point, but the order is different. Actually, ammonia has higher boiling point than phosphine and arsine. Phosphine has the lowest boiling point. Arsine next higher boiling point. Ammonia has higher boiling point than the first two hydrides. Then comes antimony hydride. Then comes bismuth hydride. This irregular observation in the case of ammonia. Ammonia has boiling point higher than phosphine and arsine is due to the association of ammonia molecule through intermolecular hydrogen bonding. Hydrogen bonding is possible in ammonia, which is absent in phosphine, arsine and other members. So because of hydrogen bonding, ammonia molecules are associated through stronger hydrogen bonds. Hence, the boiling point is higher than phosphine and arsine. So, lowest boiling hydride is phosphine. Highest boiling point for bismuthine. Similarly, the order of melting point also. Melting point also, if you compare the melting point of ammonia and phosphine, we see that ammonia is having higher melting point than phosphine. Phosphine is the lowest melting hydride of group 15. Ammonia has higher melting point, again due to intermolecular hydrogen bonding. Next, let us discuss about the oxides. Oxides of group 15 element. Oxides of group 15 element, they form two types of oxides, trioxides and pentoxide. Oxide of the formula E2O3 and oxide of the formula E2O5. Trioxide and pentoxide. Oxidation state of the group 15 element is different in the two. In trioxide, the oxidation state of group 15 element is +3. Oxygen we know -2. So the oxidation state of group 15 element should be +3. In pentoxide, oxidation state of group 15 is +5. When we compare the acidic character of these hydrides, acidic character can be explained in terms of electron deficiency. Acids are electron deficient substance. They act as electron pair acceptors. Acids are electron deficient, hence they are electron acceptors. So this can be connected with the oxidation state on the central atom. Acidic character directly proportional to acidic character directly related to the oxidation state of the central atom. Higher the oxidation state, greater the acidic character. As the oxidation state on the central atom increases, electron deficiency increases, hence acidic character increases. That means when we compare the acidic strength of E2O3, trioxide and pentoxide, which will be more acidic? The one having higher oxidation state. That is, here +5 oxidation state, here +3 oxidation state, means pentoxides are more acidic than trioxide. For example, if you write N2O3, nitrogen trioxide, nitrogen pentoxide, which will be more acidic? N2O5. Because in N2O5, nitrogen is in +5 oxidation state. Here nitrogen in +3 oxidation. So as the oxidation state increases, acidic character also increases. If you compare the acidic strength of trioxides down the group, that is N2O3, trioxide of nitrogen, P2O3, phosphorus trioxide, then arsenic trioxide, antimony oxide, then bismuth trioxide. We know that nitrogen and phosphorus are non-metal. Here we are comparing acidic character. Acidic character down the group decreases actually. Acidic character down the group decreases because we know nitrogen and phosphorus are non-metals. Non-metallic oxides are generally acidic in nature. These two are predominantly acidic. Arsenic and antimony, we know they are metalloids, possess both metallic and non-metallic character. Hence, these oxides are amphoteric. Means they show both acidic and basic character. Bismuth is a metal, we know. Metallic oxides are basic. So, down the group, acidic character decreases or basic character increases. Now, let us discuss about the halides. Halides of group 15 elements. Group 15 elements form two types of halides, that is trihalides of the formula EX3 and pentahalides of the formula EX5. For example, if you write the halide of nitrogen, nitrogen form a trihalide of the type NCl3 or NBr3, etc. But nitrogen does not form pentahalide. Nitrogen does not form pentahalide. Pentahalide is not known for nitrogen. Why? Because we know nitrogen maximum covalency is 4. Here to nitrogen to form 5 bond with a 5 halogen atom is not possible. So nitrogen does not form pentahalides. All the other group 15 elements form pentahalides. For example, phosphorus can form PCl3, trihalide and pentahalide, PCl5. When we compare the covalent character of these halides, if you compare the covalent character of these halides, pentahalides are more covalent. Pentahalides are more covalent than trihalides because in pentahalides the oxidation state of here phosphorus is +5. In trihalide the oxidation state is +3. We have a rule to compare covalent character, that is Fadjan's rule. According to Fadjan's rule, greater the positive charge on the cation, greater the covalent character. So here phosphorus carry +5 charge, hence PCl5 is more covalent than PCl3. Pentahalides are more covalent than trihalides because in pentahalide the oxidation state is +5, trihalide the oxidation state is +3. Next we have some important compounds of molecules and compounds of group 15 elements. If you discuss the first one about nitrogen. Nitrogen exists as diatomic, that is dinitrogen. Nitrogen molecule is chemically inert at room temperature because of triple bond. Nitrogen bonded to the other nitrogen through triple covalent bond. Its bond enthalpy is very high. High bond enthalpy. Hence, dinitrogen is chemically inert at room temperature. At sufficiently high temperature, it becomes reactive. Preparation methods of nitrogen, it can be made, very pure nitrogen can be made by the decomposition of barium or sodium azide. Barium azide, when decomposed, we get barium and dinitrogen. Similarly, sodium azide also on thermal decomposition produce sodium and nitrogen gas. This way we can prepare pure nitrogen. Very pure nitrogen is prepared by heating sodium or barium azide. Then an important compound of nitrogen is ammonia, NH3. Ammonia is manufactured from nitrogen and hydrogen. The manufacturing process of ammonia is called Haber process. Dear children, note down the conditions of manufacture of ammonia by Haber process. The conditions are temperature and optimum temperature of 700 atmosphere, 700 Kelvin, 200 atmosphere pressure, and presence of iron oxide catalyst with small amounts of K2O and Al2O3. The conditions for the manufacture of ammonia in Haber process. Ammonia has got pyramidal structure with nitrogen at the apex of the pyramid, hydrogen atom at the triangular base, trigonal pyramidal structure, nitrogen carrying a lone pair electron. The bond angle is 107.8 degree. It contains 3 bond pairs and 1 lone pair. If you talk about the oxides of nitrogen, nitrogen form many oxides. The oxides of nitrogen are N2O, NO, N2O3, NO2, N2O4, N2O5. This N2O is known as laughing gas, dinitrogen monoxide or nitrogen 1 oxide. If you write the oxidation state of nitrogen in this compound, in oxides nitrogen show variable oxidation state. In N2O nitrogen the oxidation state is +1. Oxygen we know -2, so it is +1. In nitric oxide, this is called nitric oxide or nitrogen 2 oxide. This is known as nitrogen 1 oxide. NO is nitrogen 2 oxide or nitric oxide. Here the oxidation state of nitrogen is +2. In N2O3, nitrogen show an oxidation state of +3. In NO2, the oxidation state is +4. In N2O4 also it is +4. In N2O5, the oxidation state of nitrogen is +5. Means nitrogen show variable oxidation state. If you compare the acid strength of these oxides, acid strength as the oxidation state increases, acid strength also increases. Here we know N2O and NO are neutral oxides and all the other oxides are acidic. That is, acidic strength increases with the oxidation state on nitrogen atom. Here we need to also note this NO2, nitrogen dioxide, is a brown colored gas. This NO2 molecule is paramagnetic because it contains a lone pair electron. NO2 molecule is paramagnetic because it contains an unpaired electron on the nitrogen atom. This is brown in color. So when two NO2 molecule, it has tendency to combine with another NO2 molecule and form the compound N2O4. This process is called dimerization. Two NO2 molecules combine and exist as one dimer. This process is called dimerization. This dimer N2O4 is colorless. NO2 is colored. On dimerization it becomes colorless. And here you have to also note the preparation and properties of nitric acid. HNO3, the preparation method is Ostwald process. Ostwald process involves 3 steps. oxidation of ammonia to produce NO, nitric oxide. Ammonia oxidized to produce NO. This nitric oxide is further oxidized to NO2. Second step. Then this NO2 dissolves in water and form HNO3. 68% pure HNO3 is made. More purification, up to 98% can be made by using a dehydrating agent, that is concentrated sulfuric acid. The reactions of nitric acid on metal is important. Two important reactions are reaction with copper. Copper when react with HNO3. Copper when react with dilute HNO3, we get the product CuNO3 twice copper nitrate plus nitric oxide and water. Note that here the one of the byproduct obtained is NO. But copper when react with a concentrated HNO3, here also we get a copper nitrate, but instead of nitric oxide we get a nitrogen dioxide plus water. Similarly, the product of zinc with a dilute and a concentrated HNO3, you need to note carefully and study. Zinc and dilute HNO3, the products are zinc nitrate plus N2O, nitrous oxide plus water. But zinc when react with concentrated HNO3, the product is zinc nitrate, and instead of N2O, here we get NO2 plus H2O. So the product depends on the concentration of the nitric acid. Nitric acid reacts with most metals except the noble metal, that is gold and platinum. Metals like chromium and aluminium, that also you note down. Chromium and aluminium do not dissolve in HNO3 because of the formation of a passive oxide film on their surface. And nitric acid is a strong oxidizing agent. Its oxidizing reaction also very important. Oxidizing reaction of nitric acid. Nitric acid oxidizes metals, we already written, copper to copper nitrate, zinc to zinc nitrate. Metal is oxidized in this reaction. Nitric acid can also oxidize non-metals. For example, iodine. Iodine is oxidized to iodic acid, HiO3. Carbon is oxidized to carbon dioxide. Sulfur is oxidized to sulfuric acid. Phosphorus is oxidized to phosphoric acid. The other products are NO2 and H2O, which is common. Oxidizing action of nitric acid on non-metals.